I'm Marco Palladino. Today we'll be talking about microservices and API gateways. I'm the CTO at Mashape.com and one of the core committers of Khong. Khong is an API gateway, and today we'll have the chance to look how it works and how it can fit your architecture. To understand why do we need an API gateway, to understand why that it's important, I'll start talking about monolithic versus microservices architecture. So what's the difference? What's the main shift? Then I will introduce the API gateway pattern and how that can fit a microservice-oriented architecture. And then we'll talk about Konk and nginx. So one of the things that we have been witnessing in the past few years, it's a transition to microservice-oriented architecture from monolithic application. We all are familiar with monolithic applications and how they usually work. And this is a simple representation. We do have an app that pretty much includes all of the business logic and all of the entities that we'll have to deal with. And usually we have one data store that all of these entities and the app will use for storing data and retrieving data. And usually monolithic architectures can be horizontally scaled by deploying the same huge chunk of code over and over again on multiple servers. And so every time we scale the app, we are scaling all of these components all together. So it's one unique piece. And like every approach, there are like pros and cons. Monolithic applications can be very easy to build and easy to start with for smaller code bases. It's easy to start coding on them. We can build and bake everything in the same code base, which means we don't have to worry too much about modularization and how to handle different components together. It's easy to test. Usually when we are testing a monolithic app, we are starting that one application, and then we're testing, we execute our integration or unit tests. And so it's one app that we have to start, and that's pretty much it. And IDEs have a very good support for monolithic applications, right? So you can, for example, from Eclipse, you can start the app, you can test it. You have lots of tools and tooling around monolithic apps. But of course, having everything baked together into one code base, it's not ideal if you have a growing code base, right? Because over the years, the more and more features you're building, the more code you add, the harder it's going to be to keep track of this code in one place. Because of that, teams will iterate slowly on top of this huge code base. And the bigger it gets, the slower you will be able to iterate on it. If you want to innovate, let's say I want to replace a data store or I want to use a new technology. In a monolithic app, that's usually painful because you cannot isolate a specific use case, implement, for example, a new data store. It's harder to do it and then push it online. And because of all of this, if you're scaling the organization, you're scaling the team, it's going to be harder for a team to understand what the code base does, and it will take a longer time for a new team member to get up and running with the code base. And so what we're witnessing here in the past years is this transitioning to microservices. And containers are also helping in this transition because they create a great tooling around microservices, but I'll talk about that later. Microservices, you have the app split in different components. So instead of having a code base that handles all the entities, now you have different components, different services that are being deployed independently from each other and scaled independently from each other. And so in this example, if I have customers, orders, and invoices, these entities and these components will be deployed in their own server. The communication then can happen through multiple formats, usually HTTP or RPC. And sometimes you can also allocate different data store schemas to each one of these components. So you are isolating how the component works and make it work independently from the other components. This also means that often you will need something like an event handler and some workers. So for example, in this example, the client can create a new order, and then what could happen is instead of the client creating a new order and a new invoice, you can create a new order, and the order component will push an event, invoice created, and something else can listen to this event and then create the invoice automatically for you. So you can build an asynchronous system application that does not depend on the client, and it can work autonomously. This also means, for example, that if the invoice component is not running, then you can retry that operation later, for example. And again, we have pros and cons. Microservices are not a good fit for everybody, and not for every use case. It definitely is a good fit for larger applications. You have a large application, and now you split this large application in different components, and developers will be able to iterate, maintain, and build those components independently from each other. It's some sort of, the analogy that I'm making here. Somebody said, transitioning from a monolithic app to a microservice-oriented application, it's like having a full chicken and then transitioning to chicken McNuggets. So now you have all these little components working together, and you can scale them independently. So that's a big pro. Better agility in the long term, of course, because now that each component is doing only one thing, and that one thing only, you can easily iterate and innovate over that component without disrupting the other components. Because each component will talk to each other using an interface, like, for example, an HTTP RESTful interface, you can change and experiment with implementation, and as long as the interface doesn't change, the app will keep running. The whole system will keep running. Microservices, they are micro, which means that if you need to scale the organization, if you need to scale the team, you can start assigning these, smaller pieces of the app to your team members, which in turn makes it faster for them to understand how the code works, and they can start iterating on the code base faster. If they have to use another component, they can use an interface to consume the other component without necessarily have to dig into the code. And if something goes wrong, usually in a monolithic app, everything goes wrong. So if there is a bug, if there is a problem, usually what happens is you have high chance of the app going down or not working at all. With microservices, if you have a problem, it's a problem that's isolated in a specific component or service of your architecture, which means that only that part of your app will stop working while the other components can keep working. And so, for example, in my slide here, I was explaining how we have an order and an invoice component. If for some reason somebody is pushing a bug on a Friday night on an invoice component and the invoice component stops working, well, we can still keep track of what we have to do using the event worker. And so once the invoice component is up and running again, we can then create those invoices that have not been created because of a bug. All of this is possible, of course, to implement in a monolithic app as well. But what we're seeing here is that a microservice-oriented architecture encourages this development style, while monolithic apps tend over time to become like some sort of spaghetti apps. There are significant cons to a microservice-oriented architecture. So first of all, you have lots of moving parts. You don't have anymore just one app that runs and executes requests and does everything in one place. You now have multiple components and multiple services that have to work all together at the same time in order to have a successful product running in production. Which means that you are having suddenly more complex infrastructure requirements. Now you need to have a way to easily deploy those different components independently, to scale them independently, and to monitor them independently. That's also part of the reasons why real-time monitoring and analytics became so popular in the past years. It's because once you have a microservice-oriented architecture, you really have to monitor each one of these places and have one central place where you can see your components running in their status. consistency and availability. So you can, in a monolithic app, you have one place, one code base that stores and executes and links all the entities together. In a microservice-oriented architecture, you have different components. Each one is dedicated in doing one thing and just that one thing, which means you now have an availability problem. Services can go down, may not be available, or a consistency problem. You may want to scale these microservices in multiple data centers, for example. And so you have to create an app that can take into account these new challenges. And harder to test. If you want to test the single service, well, that's easy. You will now have, so it's harder and easy to test, depending on what we're testing here. You can easily test an individual component, but it's harder to test the big picture altogether. Now, usually, if you want to test an app that's built in a microservice-oriented architecture, you have to start all of these components at the same time, so you can have them talking all together, and you can successfully implement an integration test. And so, why do we need an API gateway? And how can an API gateway help in a microservice-oriented architecture? We always hear the word orchestration. So I like this slide. It shows an orchestra with the individuals who are the microservices playing their own instrument and doing just that. And then we have the director, which is the API gateway, which somehow can orchestrate how the requests are being processed by our architecture. The API gateway pattern means putting the API gateway in front of your microservices and make the API gateway become the entry point for every new request that's being executed by the app. This can simplify significantly both the client implementations and the microservice app. Before, the client had to make a request to consumers, then to orders, then to invoices. The client needs to understand and know how to consume these different services together. But with an API gateway, we can now abstract all of this complexity and create, for example, optimized endpoints that the client can use, and the optimized endpoints under the hood makes those requests to those components. So I'll make an example in the next slide. Or, for example, request collapsing and other things like authentication, rate limiting, traffic control. So, for example, optimize endpoints. If we assume that each component returns different JSON responses, so we have a JSON response for consumer, orders, invoices, and let's say the client wants to retrieve this information, there are two ways. One, it's making a GET request to the consumer's component to retrieve the consumer, then the orders, and then the invoices for a specific order. Or we can abstract this client implementation complexity by using an API gateway. The API gateway can then expose a specific endpoint that under the hood will make those requests and then returns to the client one unique response after it has consumed the microservices. Which means, for example, we can collapse all of those responses into one response and one request. This helps a lot. It's very beneficial, especially for mobile clients. You can speed up the mobile implementations, and you can also do things like transformations. One of the nice things that an API gateway enables is the fact that the client doesn't have to know what's the address of the component. So the gateway will take care of that. You can change the implementation, and you can even change the interface, the API interface. And usually that's problematic because every time you change an API and you change an interface, you risk breaking existing clients. With an API gateway, you can effectively abstract this on a separate layer, so you can change the implementation and the interface while still keeping the public interface the same for existing clients. So you can do things like transformations, for example. And API gateways are also a great tool that help transitioning from a monolithic app to a microservice-oriented app. If you have a monolithic app, you can start putting an API gateway in front of it. And then slowly, you can start splitting the monolithic app in different microservices and keeping the clients working through the API gateway. So the API gateway will, over time, implement and consume the underlying upstream services while keeping the client working. So having an API gateway, in a way, can help this transition. And of course, creating a new optimized endpoints is just one of the benefits of having an API gateway. You can also centralize middleware functionality. As you start creating more and more services, you will find yourself in a tough spot. You will need authentication for those services. You will need traffic control for those services. Some of them will be public, some of them will be private, and some of them will be partner APIs that you want to make available to just some specific users. And so sooner or later, you will be finding yourself in a place where you're implementing the same middleware functionality over and over again inside of the microservice. I believe the microservice should not take care of this complexity and let the API gateway take care of it, which means that the microservice will be only responsible for receiving incoming requests, generating a JSON response, for example, and the API gateway will then centralize all the authentication, logging, traffic control that you need to implement in your app. And here in this slide, I also introduced last minute FAS, Function as a Service, which is the new cool thing, apparently. And an API gateway can work well with that use case as well. So in short, functions as a service means you're consuming an endpoint, an API endpoint, and that API endpoint does something somewhere. It's running on a serverless architecture. Which means on a server that's not yours. And so you can put an API gateway in front of those kind of functions as well to run that middleware on top of that as well. And so here I'm just going to show you a few use cases of what an API gateway can do for you and how it can make your life easier if you are, for example, deploying software. In microservice-oriented architectures, it's easy to deploy multiple times a day that one specific service. It's not as hard as having a monolithic application. In the monolithic app, usually deployments are slower because every time you make a little change, you have to deploy the entire thing again. And as the application grows and becomes bigger, that can become slow and problematic. With microservices instead, you can deploy software as individual components multiple times because usually it's faster and easier to do that if you have a small, if you're just deploying a small chunk. And so, if you need, for example, to implement blue-green deployments, an API gateway can certainly help in making this possible in an easy way. So, for example, if you have customers version 1 and customers version 1.0.1, an API gateway can know the location of both of these components, and then the API gateway can provide an interface for you to switch traffic from the old version to the new version. Another deployment strategy are, for example, canary releases. When you're creating software, sometimes you don't want all the traffic to go all at once to the new version of your microservice, because the microservice maybe has not been tested well, or there are like unknown problems, and generally speaking, it's not wise sometimes. And so canary releases allow you to direct only specific amounts of traffic to the new version. And an API gateway can take care of this use case. So you can decide to redirect to proxy only 10% of the request to a new version of your component. And then, once you're sure there are no bugs, it works, then you can, switch 100% of the traffic to it. Another thing that an API gateway can do, it's load balancing. Usually, actually, the load balancer could be the API gateway. The API gateway knows where all the services are located and their address and port information. So the API gateway can, there are different strategies here. You can either put a load balancer between the API gateway and the final service, the upstream service, or the API gateway is the load balancer, or the API gateway is the load balancer, and it leverages a service discovery tool like Console or etcd to load balance those requests. So, the service discovery tool will give you a new address every time you ask to resolve a new IP address every time you ask to resolve a DNS address, and effectively you're doing some sort of a round-robin load balancing at the DNS level. Or circuit breakers. Let's say that one of those services suddenly stops working and returns a very high number of errors. The API gateway can implement things like circuit breakers, which means that after a specific threshold, the API gateway will stop sending data to that component that's failing. These give you times to analyze the logs, implement a fix, and push an update. Usually, when you have a component failing and you have lots of traffic to that component, that component as well may be using other components, so you may have a cascade failure in your infrastructure. Circuit breakers simply open the circuit, so no more requests are allowed to go to that component, and now you have time to fix and implement a solution to your problem. And sometimes there is also this misconception that's very common. Sometimes product managers, software engineers, they think that building an API, it's the same as running an API. And so building a microservice is the same as running a microservice. But those are two different complete problems, and they have to be addressed in a different way. I think that building the API, it's usually the 50% of the workload required when building a microservice or an API. And then there is this other hidden 50% of the workload that not everybody takes into account, which is, OK, now we have an API running. It can accept requests and return responses. But how do we handle management, right? So credentials, traffic control, rate limiting. And then the next step is, OK, now we have a rate limiting for our users, but how do I whitelist just a subset of those users to have, for example, a higher limit? And all of these questions. And then monitoring analytics, it's very important. You need to constantly be able to monitor and track down the status of your components, and documentation. Microservices can, more often than not, can have an API that you can consume. And if you have an API, you also want to have a proper documentation. That's important not just for public developers, but for internal private developers in the organization as well. You may be a telco and have a voice API and an SMS API. And so if the two teams, one is in New York, one is in SF, you want them to work together, well, the teams just have to release a doc for their API implementation, API interface, and then anybody inside of the organization can use that API. So it's very important to be able to keep the documentations up to date as well. And this is also part of the 50% of the workload that's usually not being considered when creating an API in general, but also microservice-oriented architectures. So API gateways can fix some of these problems by implementing those middleware functions that you don't have to re-implement again in those services. Sometimes different teams implement different microservices in different ways. And so if you do not have a centralized way of doing things, you will end up with teams doing authentication and rate limiting in a different way, for example, than another team. So you want to avoid having this fragmentation. And an API gateway can also help fixing not only the management part of an API, but can also help in fixing the other two missing things that we have to do. Analytics, a gateway can communicate transparently with your analytics infrastructure to send, because the gateway is the entry point for every request. The gateway knows all the data and the traffic that's going through your services. So the gateway can, push. You have one central place where you can push all of this information to your monitoring or analytics solution, like Kibana, the Yield K-Stack, Splunk. And the gateway can also help automate deployments, but also documentations and onboarding. What is onboarding? Like if you have an API and you have authentication, you will need something that allows users to create credentials for that, for example, for that API and start consuming the API. The developer portal or your documentation can integrate with the gateway to provision these credentials, so you don't have to, build something from scratch on your own. And so what is Khong? Khong is an open source API gateway or management layer for APIs that you can use for implementing extra features on top of those upstream services. Khong is open source, so it's available on GitHub. You can download it and use it today. And it centralizes all of that fragmentation in one place. So this is shows exactly what I was talking about before, and the fragmentation of having multiple services, each one with different implementations for common features. And so an API gateway like Khong can centralize all of that in one place, which in turn makes development of those services even easier because you have less code to handle and maintain. And so what are plugins? Plugins are the middleware, the Khong middleware that you can add on top of those upstream services. Middleware plugins can be everything, can be anything starting from authentication to security to traffic control, logging, transformations. You may have a SOAP service that you need to convert, you need to make available with a RESTful interface. Well, an API gateway like Khong can implement that transformation layer in the API gateway, so you don't have to ask your team to change the implementation of the API or do that transformation there. The API gateway can implement that transformation for you, for example. Technically speaking, Khong is an OpenResty application. OpenResty runs on top of nginx and extends nginx with Lua. Lua, it's a very easy to use scripting language that allows you to pretty much script the things you can do in nginx. So for example, OpenResty provides hooks for different events of the API, the request and response lifecycle. And so you can write Lua scripting code that can hook into those events. Like, for example, a new request is coming in. A new request is about to be proxied. A response came back. You can write your custom code for each one of these events, and you can change the request and the response on the fly when a client makes a request. And so we have nginx at the bottom. Nginx is what handles the low-level features of Khong. All the proxying, it's being done by nginx. Very solid technology. OpenResty, it's the underlying core of Khong. It extends nginx with these new capabilities. And Khong, on top of that, on top of those two technologies, implements clustering, plugins, and a RESTful API that you can use for managing the API gateway. So likewise, with Elasticsearch, if you guys are familiar with it, you have an API for pretty much doing whatever you need to do for your data store. Khong exposes an API that allows you to 100% operate the system by just making HTTP calls and parsing a JSON response. This means you can integrate Khong with your DevOps and automation tools. You can also integrate Khong with third-party services or third-party developer portals and onboarding tools. Khong stores every information in either Postgres or Cassandra. And depending on the use case, you may want to use one or the other. So Cassandra, it's an eventual consistent data store, which means that if you have a cluster of Cassandra nodes and you're storing data, you're incrementing a counter, eventually that data will be propagated to all the other nodes, not at the same time. And so you can have, let's say, a Cassandra cluster of 3 nodes in DC1, a Cassandra cluster of another 3 nodes in DC2, and then link them together. And whatever data operation you're doing on one data center, it will be eventually replicated to the other data center. Postgres, it's easier to use. It does not natively support multi-DC replication. I mean, it supports master and slave, but it doesn't support masterless multi-DC replication, although there are some tools that allow you to do that. And since Konk is built on top of nginx, you will be able to access the nginx configuration and pretty much replace your existing nginx implementation with Konk and still run the old functionality on top of Konk, plus now you have also Konk on top, right? And so, this is exactly how it works. So we do have an nginx configuration that you can change, you can update, you can modify. And then Konk itself comes with its own configuration that you can include inside of the nginx.conf. And the Konk configuration, it's leveraging the OpenResty directives, like init by Lua, access by Lua, header filter by Lua. And those are all the events in the life cycle of a request or a response that you can hook into when creating a plugin in Konk. Konk already comes with some plugins that either the community or Mashape has built, and some of them are available on getkonk.org on the website or on the GitHub repo. But also, the community has extended the system with their own plugins, and so you can, if you search on GitHub for Konk plugins, you can find a plugin for other things that are not displayed on featured on the website. On the website, we generally speaking just put those that we feel are stable enough to be used in production, but there are like maybe other ready-to-use plugins on GitHub. So I encourage you, if you are planning to use Konk or to look into Konk, I encourage you to check what the community has built so that you don't have to reinvent the wheel. But if you need to do something that's very custom and it's very specific for your use case, you can, of course, extend Konk by creating your own plugin that you can ship privately inside your organization, for example. And the plugin will have access to all of these OpenResty events. So you can change requests, change the response on the fly. You can also make requests to third-party services. Like, let's say you have a legacy authentication system that you want to integrate in the API gateway. You can create a plugin that makes a request to that authentication system on every request, and then handle that in the plugin, and then return a response. So the client will just have to make a request through the API interface. And there are 2 main entry points for Konk. One, it's what we call the proxy entry point, which means consumers and clients that want to consume the upstream services will be able to do that through, by default, port 8000 or 8443, which is the SSL port. And then you have the admin API, which is available on a different port, 8001, and that's the API you can use for doing pretty much everything you have to do on the system. I can, after this presentation, I will show you quickly how to use Konk using the terminal. And it's important to know before doing that Konk has 3 main core entities that you will always use during, in the API gateway, and those entities are APIs, which represent the upstream services that you're trying to put behind Konk. So you can have 1,000 different services behind Konk, and we call them APIs. You can have consumers. Consumers are clients or individual developers. It depends what's your use case, that are going to consume those APIs. The consumer can be a client app, either internal to the organization or public or a partner. And then we have plugins. So you can apply plugins on top of APIs and consumers to change how the middleware functionality work. And so, for example, I can have plugins that are applied for every API and every consumer. Let's say I want authentication or rate limiting for every service, and I want to rate limit the request to 200 requests a second for every service. And then you can have plugins that are for every API, but for a specific consumer. So I want everybody to make 200 requests a second, but then this internal app should not have any limit. I want to disable the limit. And so you can do that for that one consumer, for example. Or per API and per consumer. Or again, per API and every consumer. So you can play with it in a very flexible way. And this is an example use case for a multi-DC deployment. So the way Konk works, Konk is the entry point for all the requests your clients are going to make. Konk will accept the request, will figure out what kind of upstream service you're trying to run, and will try to run the middleware associated to that API. Some of these middlewares can be authentication plugins. And so there is an order execution. Those will be executed first. And then once Konk knows what API, what consumer is trying to consume the API, it can load dynamically all of this information. And Konk relies on the data store just for the first request. So on the first request, Konk will parse all of this information from the data store, and then will cache it in memory. And so all the other requests that after the first one are going to be handled in memory, which means that Konk can be very fast without adding too much latency on the transaction. And if you have two different clusters, you need somehow to connect those two different data centers together. And so the information that's going to be shared, it's going to be either data between the Cassandra nodes or invalidation events. So because Konk caches everything on the first request, what happens if on another node you're making some changes? How does the previous Konk node know that that data it's not valid anymore? There are invalidation events that are being sent across the Konk nodes. And so every time you're making an operation on one Konk node, that one Konk node, for example, you're changing the address of an upstream service, that one Konk node will then invalidate that one specific entity, will send an invalidation event for that one specific entity to all the other Konk nodes. The other Konk nodes can then receive this invalidation event, delete the entity, and if a new request comes in, Konk will be forced to require the data again from the data store. And so here we go. I'll try to be very quick. I do have Konk running with Docker. And I have it. Here we go. And I can invoke it on my admin port. So this is the admin port of Konk. And so now, for example, I can tell Konk, OK, I want to create a new, add a new API, test. I want test to, here we are creating a mapping. We're telling Konk how to process requests. And so every incoming request to /test will be proxied to, for example, httpbin.org. I'm pretty sure everybody is familiar with httpbin. And then I'm telling Konk, OK, before proxying the request, strip that /test, because /test does not exist on the upstream service. Great. So now I can consume the service by executing /test and, for example, /get. /get, it's an endpoint being handled by httpbin. If I do this operation, here we go. This is httpbin answering to my requests. And these are the proxy headers that are being returned by Konk. And now let's say I want to add an authentication plugin on top of it. I want to protect this upstream service. I can use the admin API again, APIs, test, plugins, and tell the system I want keyauth on top of it. If I do this, the system will add the plugin on top of that one API. And so if I consume the plugin again, it will now complain I cannot consume the API. Now I can have one node or 100 nodes, and this information will be automatically replicated across every node. I don't have to worry about reloading or restarting the nodes. And so I can make another post request. So this is it's a CLI tool called HTTP. If I send parameters in a specific format, it automatically makes a post request. So I can create a new consumer, for example, demo. And then I can associate a credential to this consumer. For example, secret 123. If I now replicate the same request again with secret 123, the system will validate the request and proxy it to the upstream service. Now I can integrate the Kong's API with existing tools or existing applications, and Khong will automate all of this for you, including rate limiting. Right? Let's say I need to create a multi-DC rate limiting solution on top of this upstream service. Each API, each plugin can have configuration properties. So in this case, the configuration properties that I can apply are how many requests I want. And so I can tell the system I want to be able to make not more than 10 requests a minute, or a second, or an hour per hour. And so if I do this, and I consume the API again, Khong will now implement that rate limiting feature. And the real functionality here is being delivered by plugins, not by Khong per se. Khong per se is just a plugin middleware manager, if you wish. And I'm a little bit over my time, so this is it. I think maybe we have like 2 minutes extra for questions, if you guys have any question. Yes? Yeah, that helps, the microphone. Yeah.
OK, is it possible for Khong to rate limit upstream requests?
Requests to the upstream or responses sent back?
So for example, it might have 1,000 requests coming from downstream, but Khong limits the number of upstream requests to perhaps 30, therefore somehow queuing the downstream requests and only allowing a smaller number of upstream requests.
So that's definitely possible. The rate limiting plugin that I've used today does not implement that feature. But you can fork this plugin, for example. It's open source. And then implement that logic in Lua to do exactly that. The community has built another rate limiting plugin. It's called the Quota rate limiting plugin. It does not cache. It does not exactly do what you are trying to implement, but it allows you to configure from the API how you should rate limit the requests, right? So in the API response, you can set a custom header that tells Khong, the number of quotas that you want to allow for that one consumer. And so if you set that to 0, then Khong will block that consumer from making additional requests. All right. Oh, another question here. Yeah, one more.
So is it possible with Khong, let's say, for example, I don't want to rate limit a particular type of request, but if one particular request happened, let's say, for example, I had a multi-tenant system. I had lots of customers sending in requests to Khong. I had 100 customers, but one of them decides to go wild and send 10,000 times as much traffic. Is it possible to somehow queue up that customer's traffic so that it doesn't interrupt the traffic from the other customers without necessarily rate limiting it?
Sure, yeah. I believe there is a throttling plugin available. So you can check that out. And plugins can be applied per API and per consumer. So you can create a plugin configuration just for that one specific consumer, consuming that one specific API. And then you can, just for him, have like a special treatment. All right. Thank you.